This is part 2 of lecture 5 of Applied Machine Learning. In this video, we're going to take a little detour from our earlier discussion of probabilistic models, and we're going to spend this video talking about a tool that is going to be useful in the rest of this lecture called Monte Carlo estimation. This is going to be a mathematical approach that will be used both in this lecture and in several other lecture in the rest of this course. So before we define what is Monte Carlo estimation, let's establish some notation. We're going to assume that we have a random variable x which lives in some space x and this some script x, and this variable is described by a probability distribution p. This doesn't have to be a vector of features anymore. This is just any random variable. It can be either a sample from a data distribution, or it can be any random variable. It can be the outcome of a throw of a coin. It can be a roll of a dice. This is just some random variable. So if this is a random, if x is a random variable, we can compute the expected value of various functions of this random variable. So let's say that x is a roll of a die, or let's say it's the roll of two dice. So we throw one dice, we throw another dice, and we want to know their sum. G can be a function that computes their sum, and we want to estimate the expected value that the sum of the two dice throws will take. This form here gives us, this expression here gives us the definition of an expected value, and this is a basic concept from probability, and what it says here is the expected value that the function g will take, so the expected sum of the two throws of dice, that will simply equal the average value of the function g, where the average is weighted by the probability. So in other words, let's say that x can take some throw, which so let's say x is the result of throwing two dice, which can be either a 2 or a 3, or a 3 or a 4. So if it's a 2 or a 3, then their sum is 5. If it's a 3 or a 4, then the sum is 7. So here we're simply adding all the possible outcomes and we're weighing them by the probability, and this is the definition of an expected value. So expected values are really important. They're used everywhere in statistics and in machine learning as well. But computing these values can often be difficult. For example, if x takes a large number of values, then here we have to sum over a very large number of these possible values, and that may not be possible in practice. Or something else that can happen is x could be continuous. Here I made the assumption that x is discrete, and I gave the definition of an expectation when x is discrete. But when x is continuous, this becomes an integral, and we may not be able to solve this integral in closed form. So computing the expectation may be challenging. And in practice, in most practical applications, expected values are not computed exactly. They're computed in an approximate way, using approximate techniques. And Monte Carlo estimation is one such technique for computing expected values approximately. Let's now look at the definition of Monte Carlo estimation. Again, we are interested in computing this expected value approximately. And the idea of Monte Carlo estimation is going to be to draw some number of samples, which we're going to denote by capital T, from this data distribution P. And then we're simply going to average the value G here across all these possible samples. And G hat here, which is a function of these T random samples, that is going to be our estimate, our Monte Carlo estimate of the expected value. So just to give you a little bit of intuition for why this would make sense, let's assume that x here takes 3 possible values and they have different probabilities. One of them is very likely, the other one is less likely, and the last one is very unlikely. Because we're sampling these x's from the distribution P, we're going to see each instance of each possible instance of the value that x can take will occur a number of times that's proportional to its probability P of x. So if we draw, let's say, 1,000,000 samples, and the probability that x1 takes the first value is 80%, then of this 1,000,000 samples, about 80% or 800,000 will have that particular value. And so when we do this average, we're going to be averaging these numbers in a proportion that's really similar to this probability P of x. Let's make this a little bit more specific with a particular example. Let's say that we're throwing dice and we have 5 dice, and we want to know what is the expected number of 2s that we're going to roll. So specifically, let's have x be the following vector, where each component of the vector is a number from 1 to 6. So that's just the outcome of the jth die. So x2 here, if x2 equals 6, then the second die rolled to be 6. And then g of x is simply going to be the number of 2s in this roll. So for example, if this is 1, 1, 1, 1, 1, if we roll 5 1s, then g is 0. If we roll 2 and then 1, 1, 1, 1, 1, that's simply that's going to be, g will take on the value 1. If we have 1, 2, 1, 1, 1, 1, 1, that will also be 1. So you see what I mean. G is simply counting how many 2s we have in these dice throws. So we can calculate the Monte Carlo estimate of this expected value as follows in Numpy. Here I'm importing Numpy, and now I'm generating 10,000 random rolls of these 5 dice. So I'm generating a matrix of dimension 5 by 10,000, where in each cell I have a number that's going to be between 0 and 5. That's just because of how Numpy works. We're going to be using 0, 1, 2, 3, 4, 5 in order to denote the outcomes of the die, and each cell in this 5 by 10,000 matrix will contain the outcome of the jth die on different samples from this distribution. And now I want to know how many times, of these 10,000 rolls, what was the number of 2s in each of these 2 rolls. So I'm going to simply count the number of 2s in each of the 10,000 samples that we drew. So this is what this part does, and then I will average across the 10,000 samples by computing the means. And the estimate here is something around 83%. And now if I rerun this cell, I will get different values. And you can see here that I'm getting something that's closer to, that's roughly around 83%. If I want to make it a little bit more precise, I can increase the number of samples, and now it's much closer to 83%. I could even draw more samples, and you can see that now it's really close to 83. Essentially, as I'm drawing more samples, I'm getting something which looks increasingly closer to the value that I want. And indeed, this is the correct value, because if you work out the math, the expected number of 2s is going to be actually 5/6. I'll leave it as an exercise to the listener to prove that this is the correct number, but the actual expected number of ones can be computed analytically, and it is indeed 83%, as this Monte Carlo estimate is saying. Now I want to highlight a few properties of a Monte Carlo estimation. As I mentioned earlier, it's an unbiased estimate of the true expectation. And by this, I mean that as we draw more samples, on average, our estimate, our Monte Carlo estimate, it will equal the true value of the expectation. In the earlier example, what this means is that the numbers that I was generating, sometimes it was 84, sometimes it was 82, but they were always, their mean was around 83%. And finally, as we collect more samples, the variance of this estimate decreases. And this is again the example that I showed you earlier. When we looked at 10,000 examples, the estimate would be between 84 and 82, but then when we increased that to 1,000,000 examples, we were now only changing the decimals of 83%. So as we collect more samples, Monte Carlo provides us with a more accurate estimate of the true expected value. So in summary, we've defined here a tool called Monte Carlo estimation, which can be applied to many areas of machine learning where we need to compute an expected value. It's a very simple and approximate method that works for any probability from which we can draw samples. In the next video, I'm going to show how we can apply this technique to an important machine learning problem.